Hi, John.
Hello, Peter.
Welcome to the podcast, Everyday Metallurgy.
Yeah, thank you. Good. I'm glad to be here.
Yeah, John, I invited you because I started to insult you. Uh, you you made a post on LinkedIn with where you shared a new process of making powder. I have never heard of it before. I've been working with metal powder for 30 years, and I didn't believe it. And I wrote uh, something not so nice to you. But then you replied very politely, and I had to reflect over what I did and said, my purpose of making this podcast is to spread out curiosity and not to spread out bad words. So I came back to you and said, sorry, I, uh, I would like to learn a little more. Uh, so now I am taking all the bad thing on my shoulders, and all those people who are listening, they can just blame me and then take the curiosity and see this podcast episode with you. So thank you very much for accepting, even though I was not very good in our first meeting.
I think you're being too critical. I think you were being very skeptical, which is, kind of what engineers do.
Yeah, but today I will only have my curiosity with me because I would like to learn a lot more about what you do at Metal Powder Works, the company that you have you're co-founder of. So could you give a short introduction to yourself and the company?
Sure. Yeah, so I'm a materials engineer by training. I live in Pittsburgh, Pennsylvania, with my family and my two golden retrievers. And we found my partner and I, Chris Aldridge, founded the company about 8 years ago, after we had pretty extensive history with additive manufacturing or 3D printing, using a lot of powders. And I think that kind of came from, what we perceived as this problem of inconsistency with the powders that we would get to use in the printers. And so after we left that business, we independently sat down and we were like, well, maybe there's a better way. Is there a better way to make powders? And I
Yeah,
had studied powder production, for more on an application basis, not in a fundamental level. So we went off and did some math, and our math tended to agree if we could do certain things, then we should be able to solve these problems. And I had really looked into process economics, again, being kind of a materials and process engineer.
yeah,
And so the math tended to agree, but then we had a problem of how would we physically make the math work? And then, that was the second part of, the project, which was, okay, well, how are we going to go do that? And then, so we slowly, worked at it. And, I always like to point out that we started Chris is a mechanical engineer. So we started in his shed, in his backyard. And we made a gram, and then we made 10 grams, and then we made
yeah,
100 grams, and then we made a kilogram, and that was very exciting. So we
yeah.
moved into our own facility, and
Mhm.
now we're here in Pittsburgh when we decided to move into a production basis. But we've been a classic kind of bootstrap startup. We've not raised $1 bajillion, and getting the word out about what we do is kind of where we're at, making
Yeah.
people aware that we're here,
Mm.
and that we've got a different process. And it's not to say that other processes are bad, but I like to tell people, there's more than a dozen manufacturing processes that use
Mm.
powder. Why would
Yeah.
we think that one method to make powder is the only solution? So
Yeah. Yeah. Can we start digging a little into what is the reference? What is the state of the art today? Because I have been working with metal powder for many years. It's press and center, it's metal injection molding, it's 3D printing, it's HVOF, high
Mm.
velocity spray deposition. But the majority of that powder is made with atomization. You melt it and you atomize it, like I show on my tie here, where atomization is the core process in spray forming.
Yeah.
Um, what is it that differs from that? What you do?
Yeah, ours is kind of the inverse, I would say, in a lot of respects. It's similar in that if you look at like the IGA atomization process, they use a bar. Well, we use a bar. The difference is we're not melting it to achieve the particles. We're using a mechanical method to create the particles. And so, the size is very important in powder production, and atomization produces a wide size range.
Hmm.
And as long as you have markets for all of those sizes, it's obviously not much of an issue. So you generate a lot of material and then you go through and you sift through it. Our process, because it's more math and mechanical, we just make what you want. So inevitably we focused on additive manufacturing because it is really fixated on, I'll say 20 to 63 microns. Some people want a little bit less, some people want a little bit more, but generally speaking, that's the range that they want. And if you look at an atomizer, it could be as low as 30% of the yield to, maybe 50%, depends on
Hmm.
the material.
Yeah.
And so our process, almost entirely everything that we make is in that range because we use math and we can, it's a mechanical method, so it's
Yeah.
very, very consistent. And so that's predominantly the big difference in that we don't melt the material. It's not an
Yeah.
atomization method by definition. It's
Hmm.
it is a particle formation method, but it's not atomizing because we're not melting something and then causing that molten metal to break up into smaller particles, which solidify as they fall to Earth. And yeah, so that's conceptually that's the big difference.
Hmm. Yeah. Can you show how it is produced, or can you describe it a little more detail? Because
Yeah.
I need some pictures. That's also why my podcast is not only words; it's also with a picture on, because I'm more visual.
Yeah, we did put this video together. I'll share this.
Yeah.
And so we had to do an animation because the physical way that our machine works, you can't visually see it. On top of which, we're making 40 micron particles, which are not easily visible anyway.
Yeah.
Um, okay, so we made this video. So it is partially a video of how our process works, coupled with some
Hmm.
animation because the way, obviously for safety and for protection of the particles, we have where the particles are made is shrouded so that we can whisk them away safely and keeping the chemistry consistent.
Hmm.
But we produced a simulation so that we could show that. So typically, the way the process works is that we're using a bar. We put that into the end of the machine here. So today, this is how we started off. In the future versions, we will move away from this method a little bit. We rotate the bar at a couple thousand RPM. We do a skim cut, so we take off any surface contamination.
Okay.
And then here's that process. So here's where we're going to go into the simulation.
Yeah.
So in that gold piece, the bar is now rotating inside of that, and
Hmm.
that is connected to the cyclone. So now we're vacuuming away the particles that are being generated. We have a linear tool at the top, and that has hundreds of teeth to it. So
Okay.
we control the frequency that we contact the rotating bar. And we
Yeah.
do that today, and we generate about 4 million particles a second. So the dynamics are fairly significant.
Hmm.
And so the teeth are the same, the rotation is the same, everything's controlled by math. And so,
Yeah.
we're generating these particles. As you can imagine, there's very little, some range in shape, but not much. We
Hmm.
have the ability to control the shape a little bit and the size, obviously. And so we've
Yeah.
produced things like flakes and fibers, but nobody seems to be particularly interested in that.
Mm.
But this is, if you walk up to our process, you will see this is what you'll find at the end of it is the cyclone is pulling the powder out.
Hmm.
That is what it looks like. You can put your hand on it. It's a no melt process,
Yeah,
and
it's
then we
cold.
drop that into a check screen, and that's where we basically
Mm.
vibrate it off, and about typically 95% or better of what we make will be in that 20 to 63 range. So 5% typically is particles that got stuck together, somewhere through the process.
Yeah. And the secret in this is the tool design and the tool material, I guess.
It's not so much the material. We're not really using exotic materials there. It's
Mhm.
conventional cutting materials. It is very
Okay.
much the tool geometry, but it's
Hmm.
also the I'll say the process dynamics, the math
Mm.
behind all of it. So the frequency that we control and the amplitude, those are
Mm.
key aspects of not only our patent but also our know-how.
Yeah. When I look at that and you talk about these temperatures, what might differ and what is pretty important these days is the energy consumption compared to a melting process. To go to 1500 plus degrees C instead of what you do cost a lot of energy. Do you have some values on the energy savings and the CO2 savings that you can do with this?
We do. We did a life cycle assessment with a local firm here in Pittsburgh,
Mm.
and I don't remember the exact numbers, but something like we emit 90% less CO2 than an atomization process. And that's partially because we're not melting the material or we don't use
Mm.
a lot of electricity. But the other part that I learned about it is that the gas, there's a lot of CO2 emission associated with gas production, transportation, and then
Yeah,
utilization. As you
yeah,
know, you use an awful lot of gas
yeah.
to atomize.
It's, yeah,
And
especially if
then
it's an inert gas like argon.
oh yeah.
That's awful.
And then the other piece that we have is that yield, so when we're hitting 90%, 95% or
Hmm.
better yield, it just
Yeah.
means that we're conserving what little energy we put into it.
Mm. Yeah. And the morphology of it, typically when you gas atomize, you can make perfect spherical particles. I made an episode a few months ago on ultrasonic atomization to make perfect satellite-free spheres. How close are we to have something that flows perfect?
So this is the education piece of I'll say in the additive manufacturing market. I don't, it tends to be newer than, let's say, maybe the industry you're familiar with is around press and center. So I've come into things from the additive piece. And
Mm.
so I think when people talk about flow and movement and spread, there's an immediate default to Hall flow. And admittedly, our
Mhm.
powders don't like to Hall flow, but then a lot of powders don't like to Hall flow.
Yeah.
That doesn't mean that they don't move. And so
Mm.
when we see the movement in a printer tends to be more spreading, which is more of
Mm.
an avalanche type method. So we
Mm.
prefer the rotating drum method for characterizing the materials. We find that tends to be very similar to what we would see in a printer. Spreading wise, our powder moves perfectly fine. Now we've tried numerous different printers,
Mhm.
from dosing wheels to rollers to
Mm.
recoater blades, and then in more forced gas situations, whether it be cold spray or a directed energy deposition technique.
Yeah.
And so we don't have any problem with movement.
Mm.
I think it is generally true, as I like to tell people, big things flow better than small things, and round things flow better than non-round things.
Mhm.
Um, but I think the world seems to be stuck on that there's spherical and not spherical, and I think the
Mm.
reality is it's a continuum. You're not, there's the super round particles that everybody likes to see the nice SEM image of, but there's a lot of other things that go into powder behavior, and
Mm.
then and that's where we tend to be in that zero point 0.7 to 0.85 sphericity range. So we're an equiax particle. We are prismatic. There's a lot of different ways to describe it.
Mm.
Um, I think that I always like to tell this story, to people that are somewhat familiar with powders and the manufacturing processes. So
Mm.
my daughter was going to college 2 years ago, and so I said, well, boys are like powder particles. There's big ones and small ones and round ones and not round ones, and sometimes they have satellites on them. They wear a baseball cap, whatever. And they
Yeah.
have their own individual characteristic.
Hmm.
But then, just like powder, if you have a population of powder, there's a certain percentage that's dominated by, maybe the really small particles.
Hmm.
So just like, some boys control the population of how their group of friends behaves. But
Yeah.
then I said the thing that most people leave out is that the process actually exerts a force on the powder too. So if you think about a powder bed process,
Mm.
whether it's binder jetting or laser powder bed, the laser's now coming in or the binder's coming in, and it's exerting a force onto that powder.
Mm.
So if the powder's highly flowing and we put a force on it, it's going to move out of the way. And
Yeah.
so that's naturally where,
Mm.
this the part of this human side of it disintegrates, which is, I say, now add alcohol to the population of boys and you might see a different characteristic yet again.
Yeah.
So the point being that we can't divorce the process from the
Mm.
powder behavior. And
Mm.
so if you it seems to me like what we want something is that moves good enough but
Mhm.
not always really well. You actually want it to be in place so that you can do work on it. And we
Yeah.
did a project with Carnegie Mellon here. I'm an adjunct professor at CMU, and I was able to go to Argonne National Lab, and we created a small binder jetting, and we shot the beam through the powder bed, and we watched as the binder came down, and we could image the highly flowing powder. When the binder came down and impacted the surface, the powder flowed out of the way. It
Mm.
like bombarded the surface, and
Yeah.
so the
Yeah.
powder
Yeah.
moved. The
Yeah.
powder that had really bad flowability characteristics, it
It
didn't go
stayed.
anywhere. It
Mm.
just compressed,
Yeah.
which ultimately is kind of what you want. And so
Yeah.
you want somewhere in between, right? You
Hmm.
don't necessarily want to be disturbing the powder. And so I would say there was zero intent on Chris and mine's behalf to create a particle that did this type of behavior. But I think now we're trying to understand how our powder might behave in those processes. And we don't have any issue with spreadability. We don't have any issue with movement of the powder.
Mm.
Um, there, yeah. So that's a big piece of the industry that's out there, is that people are
Yeah.
convinced that things
Mm.
need to be round. And I always just question people, like, do you need it to be round because that's what you're used to seeing, or is that what the process
Yeah.
really
Or
wants?
or maybe it's because round. If you make it with two tops, you can make a higher packing, so you can have a higher powder density and have less shrinkage when you laser weld it. Do you have some relative numbers on where you are on powder density, the apparent density?
The apparent density, yeah, I mean, we're in that 45% range, and I think that the main advantage that we have is that we tend to see our powder doesn't move around. So when you look at like spatter,
Mm.
for example, there's no way to my knowledge anyway,
Mm.
there's no way to measure that. But just by observation, when we look at our powder compared to a spherical powder with higher flowing characteristics,
Mm.
we just see a whole lot less spatter. And
Yeah.
so it seems like we're getting that benefit of the powder moves into position. So I always make the analogy of river rock. You can
Mm.
move river rock and it tends to sit there and just sit on top of each other, which is if you have billiard balls, well, they like to keep rolling.
Hmm.
And so that's a bit where we are coming in, and there's some advantages that we've found too, which is around like highly reflective materials. So we did some work with copper completely unintentionally. We learned through our work with the University of Waterloo. They said that they were like noticing that they could drop the power when they printed with our powder. And so we went to NIST and we measured reflectivity of the powder,
Hmm.
and we
Yeah.
found that our copper powders were absorbing 90% of the laser light as opposed to reflecting it, which
Yeah.
meant that you could drop the power as much
Yeah.
as
Of course.
40%,
Wow.
which means you're not just dumping, excess energy, because,
Hmm.
copper's tricky because of the emissivity.
Yeah.
It takes a lot of energy to get it molten, but once it's molten, you don't need the same amount of energy to maintain it.
Mm.
So when you're that's the bad news when you got that molten pool. You're dumping way too much energy into it, which means you're evaporating the copper and
Yeah.
the other
Mm.
elements. Anyway, so we I think, we don't know, but because we're doing this mechanical method with our powder,
Mm.
the surface has kind of this micro texture to it, which seems to allow the laser to couple very well with it. So
Yeah.
whether it's bouncing around or, I'm not sure the exact mechanism. Um,
Mm.
so so there's
Uh,
actually some advantages of not having a round shiny object.
yeah. Um, so now you're getting into alloys, and it could also be something about oxidation level, where I could imagine as you are in a cold process, you don't need to protect the powders if you are in high sensitive material towards oxygen. I have seen many places where when you atomize, everything is protected in argon or nitrogen to avoid oxidation while it's still in elevated temperatures.
Hmm.
Um, do you have some ideas on the level of oxygen you have, and does it differ?
Yeah, so for once in my life, thermodynamics is on my side.
Yeah.
So we are creating a new surface, so we will pick up some oxygen, just to create that,
Mm,
thin oxidation layer. Um, in our sense, that tends to be good because we're operating at room temperature or very close to room temperature.
mm,
So being able to control that oxidation behavior is really, really important. So we'll find that the theory that I'm putting out there anyway right now is we're forming an oxide layer at room temperature, maybe 100. Let's say it's 100 degrees C, but to
mm.
aluminum that's kind of nothing. To titanium it's nothing.
Yeah.
So you get what you want, which is you're passivating the surface,
Hmm.
which
Yeah.
then provides an immediate deterrence to further
Hmm.
oxidation. So
Yeah.
we do measure some oxide pickup, but it's 20 and 40 ppm. It's not very much. It
Yeah.
varies by
It's
material.
extremely low. Yeah. Especially for
Yeah,
those alloys.
that's right. And
Um,
we do take different precautions for different materials. So aluminum, copper, we run in air. We can get away
Mhm.
with that. For zirconium, for titanium, we do run those with a different collection system because they're just due to the nature of those materials.
Yeah. Now we're digging into the alloys, and that is very interesting. What alloys have you been working on? Is it only exotic, or are you also doing things like stainless steel?
Yeah, we started off doing aluminum and copper, and we do we found that most of the high strength aluminums, the 7,000 series, 2,000 series, process the same. We've done 6,000 now, 6061, 5083, aluminum scandium we can do. So
Mm,
most of the raw materials we don't really have an issue processing.
mm,
We've diversified copper away. We can now do pure copper, the low oxygen, C101. We've done copper nickel, nickel aluminum bronze, so some of the bronzes which are now of interest for some of the Navy applications. And then we've moved into zirconium and CP tie, so grade 2 titanium. And
yeah.
those other two were as a result of partnerships that we built with other companies. Otherwise,
Mm,
they're a bit special, for us to
yeah.
wander into.
Hmm.
We've tried stainless steel in the past. We don't. So if you go back to thinking about our process as a Venn diagram, we have the metallurgy of the bar. So we can
Mm,
do certain things to the bar to make it more suitable for our process. We've got the
hmm.
tooling, the tooling geometry, tooling materials, and
Yeah.
then we've got the process dynamics. And so the
Mm,
intersection is really where our process wants to exist.
mm,
And so currently where we're at is we can do these any material that's machinable, readily machinable, our process has no issue with. As
mm,
we're learning, we've moved into some of the tougher materials like zirconium and titanium. Then you
yeah.
move into hard materials like, let's say, an Inconel or some of the steels. And
Hmm.
so that's that's much more complicated because you now have to have a very rigid system. Just like in machining, you don't use the
Mm,
same CNC machine for nickel superalloys you do for aluminum, for example. Our
Yeah.
process would be similar in that the
Mm-hmm.
stiffness has to be there, otherwise you're just bouncing off the
Yeah.
material.
Mm.
So we're kind of existing in that range at the moment, which is, free machining to tough, and that's where we're living at the moment. Ultimately, I think if we have a material solution, a conditioning solution, and a tooling solution, we I'm not going to say we could make anything. And
Mm.
I think this is also kind of comes back to the atomization piece. There's some materials that atomization does quite well. And when you've got homes
Yeah.
for all of the powder sizes,
Mm.
that's fine. And that's why we've chosen not to go down like 718, for example. I think
Yeah.
atomization services that industry quite well.
Mm-hmm.
So there's really no reason for us to go down
Yeah.
that path. We're not solving a problem there. But
Mm.
where we do solve a problem is where maybe additive manufacturing is the only need for powder. And so now you've got 50
Mm.
to 80% of your production volume
Yeah.
with nowhere to
Mm.
go.
Yeah. I could imagine talking about not necessarily going into melting. Refractory metal could be next level, because niobium you have to go to above 2000 degrees C to melt it, and that's almost impossible.
Mhm.
So if you could machine that, I don't know if it's machinable. I've never worked
Yeah,
with pure metals in that group.
I'm optimistic there. I think that there is niobium is soft. It's kind of gummy. It's very tough, and so it's in a lot of ways it's like titanium.
Yeah.
And so I think I'm optimistic that we can come up with a solution there. Um, I think that's where uh, I like to tell people all the time, like, well, we're great at small runs. I mean, we're
Mm.
good at long runs. It's a mechanical process. It's continuous. We've actually done some experiments now where we leave the machines running and we leave.
Mm.
It's that efficient, that we can kind of, and very automatable, because it's really just math and mechanics, and
Yeah.
so that's goodness.
Mm.
Um, but the, I think that's the interesting part for me is like we know what we know now. We don't know where we could ultimately go. I think
Mm.
that's the question, but we need to be solving a problem for somebody. We're not just
Yeah.
going. We're a powder producer. We're not an alloy inventor. We don't
Mm.
have an opinion about which alloy is
No.
better.
No.
We're quite
Uh,
happy to make whatever.
yeah. But a material like tungsten, that's the king of melting points. Could be interesting to bring into to a process like that. And there are I know several applications of tungsten in additive manufacturing. So it could be next level.
Yeah. I think that to me, that's what I like about it because it poses some challenges. But as I we were talking before we started, the bar itself, there's things that we can do to the bar to make it more conducive to our process.
Mm.
So whether it's heat treatment, could be cold work or hot work,
Yeah.
effectively, there's still some, I'll call it
Mhm.
metallurgy, some material science, which
Yeah.
goes on, which is we can
Mm.
process the bar in different ways to get
Mm.
different microstructures to yield a different result. Most people are going to then remelt the particles anyway, so they don't really
Yeah.
care.
Yeah.
And that's a win.
Mm.
And so that's where I'm really optimistic is that as we get we try to engage more with the universities to think about, okay, today, most of the time with wrought bar, you're doing one of two things with it. You're machining it or you're forging it. And
Mhm.
so we've developed that wrought bar for those two particular outcomes.
Yeah. Um, but I had, before we started talking, I had the imagination that hardness is your enemy. So if the material is hard, you're not able to machine it. But even many hardened steel types, if we go into to the world of tool steel, you can purchase bars in soft anneal condition. So
Hmm.
a lot of tool steel is machined under standard conditions and then hardened to get the properties you want. So you might be able to even make pretty tough tool steel with that process.
Yeah.
Um,
Yeah, it's that whole chain that's important. What our customers are going to do with it, then maybe that can be heat treated, and then that's
mm,
ultimately the
mm,
what the where the hardness, comes in, or the properties come in.
mm, yeah. Then John, I'm working in the world of scale. So if I have talking present center a customer that asks for two pieces, I'll send him to the 3D printing guys. So I need volumes. We typically talk tons. Where is the limit? What is the scalability of your technology?
Yeah, so I think one is, I think about, we're working right now. We've actually just doubled the capacity of our machine by moving from a tool that's 1.5 inches to 3 inches. And so
Hmm.
something as simple as that just
Yeah.
doubled the capacity of a single machine with almost
Hmm.
no investment. So
Yeah.
you think about the continued increase in scale that we have just from improving the efficiency of the unit. So we'll keep working on that.
Mm.
Let's say that we could grow it by 10 times. I think that's a reasonable figure to get to. Simultaneously this year, we're working on what we call the next gen system. So the video that I showed, that's the first ever version that we ever came up with. And so
Hmm.
as a startup, it's not easy for us to design, manufacture, and assemble something. So we
Hmm.
bought, something that we use 20% of. So
Hmm.
now we're in the process of looking it's a very creative name. We've come up with the next gen machine. And
Yeah.
so we're we went through our PDR, and we believe that we can get to 25 times productivity over our current system. That's the initial operating point. We believe that
Uh,
the upper end
25
is
tons in a year or in
25 times, excuse me.
okay. Yeah.
So
Uh,
so we can this year we'll round out the year with the ability to make 7,000 kilograms. Leading into next year, that would become 40,000, and then moving from there. So we have
mm,
two levers, right? One is the system itself and the number of
mhm.
systems that we have.
Yeah.
The other piece that I like to point out to people is that if you do the math, and let's say that you have an atomizing facility that, let's say, it does 250 metric tons, but you need 20 to 63 microns, so that's maybe 30%. So
Mm,
that means that you have to make 250 to get to 75.
yeah.
We make 100, but we're
Mm,
95% efficient, so we get 95 tons.
yeah.
So, I always task people with, let's make sure that we're comparing apples and apples,
Mm,
not apples and oranges. And so our output can be lower because our efficiency is very, very
mhm.
high.
Yeah. I might have a project. We have to talk on offline afterwards.
Sweet.
uh, John, my podcast is called Everyday Metallurgy because I would like to relate it to where do people see this in their daily life, or if it's not there, what are we missing? Can we feel this somewhere?
Yeah, I think that, I mean, certainly, if you ever come to Pittsburgh, you can come see it for yourself. I think that everyday life piece is something where I I love additive manufacturing. I've been a proponent of it for years, and
Mhm,
I think that the challenge is when from having worked at Lockheed Martin and Honeywell, if you have to change the process and the material, that's a very difficult thing to have to go do. And
mm,
so when I went, and a colleague of mine, we went and looked up the AMS specifications for powders. Well, there's 16 of them. But if you
mhm,
look it up, the AMS specifications for bar stock, there's over 2,000 alloys in there.
yeah.
So I think I look at, like to bring it back to the everyday thing, which is
Mm,
the average engineer doesn't want to, they're okay changing the material or the process, but they don't want to do both. So if we provide a mechanism for them to keep the same alloy that they're used to doing,
Yeah.
and they've got a lot of experience with,
Mm.
I think there's an efficiency there, which is we don't, you know, let's put it said differently. If you're an economist, if you
Mm.
tried to buy 2,000 atomizers, it would be really expensive. Our process, our capex cost is a fraction of what
Mm.
an atomizer is. So that's where I would like the everyday piece to come in, which is I would like to enable people to use the materials that they're used to using, that they have a lot of experience
Yeah.
with.
Mm. I fully agree. That is one of the major obstacles for getting powder metal into the world on a wider spread, because there is a limitation on number of alloys. So people have to, yeah. It's like the old day when Ford invented the car. You could have it in any color you want if you want it black.
Right.
um, then my last question for today is, where could people learn more if they want to dig deeper into the technology?
Yeah, I mean, the first best place is our website, metalpowderworks.com. And then we are increasingly out at more events. We just came back from the Cold Spray Action Team meeting
Mm.
that was here. Um, we've had presentations at TMS and Rapid, and mostly through our partners at University of Pittsburgh and University of
Mm.
Waterloo. So we would like to work with more universities, because that's where we have a new process. So getting fundamentals understood isn't something that
Mm.
we're great at. Um,
Yeah,
and learning how the process ultimately works is goodness. So I would say, that, and of course, people are just happy to write us with questions.
perfect. Thank you very much. I really enjoyed it, and I learned a lot. Uh,
Good.
so I hope you will help spreading the word on the episode.
Yeah, that'd be great. And if you do come to Pittsburgh, we'll pick you up at the airport. We're literally 5 minutes.
Fantastic. Thank you.
Okay, thanks, Peter.